we calculate delta G values? Well, just like we had a table for delta H knots of formation, and we have a table for S knots for standard entropies. So we got a standard enthalpy table, standard entropy table. We're going to have a delta G knot, a standard free energy of formation table as well. So the change in free energy that accompanies the formation of 1 mole of that substance from its constituent elements with all reactants and products in their standard states is just going to be the sum of the free energies of the products minus the sum of the free energies of the reactants. And we can do that because this delta function is a state function. Right? So we're just going to do, right, this is really just saying final minus initial, but a little fancier. Let's look at another example. So methanol is a high-octane fuel used in high-performance racing engines. So if you've ever been to a monster truck rally, right, they're going to be using methanol as their fuel. So we're going to calculate the delta G, or free energy, for our following reaction. We got 2CH3OH, that's methanol, plus oxygen is going to give us CO2 and H2O, our standard combustion products. We're going to use the following free energies of formation. The CH3OH, or methanol, is going to be minus 163. Our oxygen is 0. So remember, just like we had those standard enthalpies of formation, any element in its natural state is going to be 0. Our CO2 is going to be 394. And then our water is going to be minus 229. Right, we're just going to do the sum of the products minus the sum of the reactants. Our two products are the CO2 and the H2O. We've got 4 H2Os and 2 CO2s. And then we're going to subtract the sum of our reactants. We had 3 oxygens, but those are easy because those are 0. And 2, oh man, they did this in a dumb way. Yeah, I would have just bracketed this and had these guys as pluses. There we go. But they're doing a minus and a minus. If you want to do it that way, that's cool. However you do it, as long as you're doing it right, it's not going to bother me. So you're going to get 2 moles times minus 394 plus 4 times minus 229. So you're going to get 3 times, minus 3 times 0 minus 2 times 163. So you're going to get minus 1,378 kilojoules as your Gibbs free energy. Delta G is negative, and it's going to be very highly favorable thermodynamically. So that is going to be the spontaneous. So the chemical engineer wants to determine the feasibility of making ethanol by reacting water with ethylene according to this reaction. So we're going to have our ethylene reacting with water to make ethanol. Is this going to be spontaneous under standard conditions or not? Again, this is one of those ones where we're going to have to keep attention to what these phases are, right? Liquid or a gas, because it's going to matter. All right, to determine the spontaneity of the reaction under standard conditions, delta G, we're going to look for, on the table, for our values for both our ethanol, our water, and our ethylene. And notice some of them could be negative, some of them can be positive. We're going to take some of our products, our ethanol, and then we're going to subtract the sum of, oh man, that's just bugging me. All right, do it that way. Minus the sum of the reactants, right? And we're going to end up with minus 6 kilojoules, so it's just barely spontaneous under standard conditions at 25 degrees C. Does that make it economically viable? Probably not, because where are you going to get that ethylene from? But it is spontaneous. So let's do another stable concept check here. Stable diatomic molecule spontaneously forms from its atoms. So I'm going to take a nitrogen, get N2 gas. Is that going to spontaneously happen? Let's predict the following signs and then explain. Welcome back. So our enthalpy change. So this reaction is going to be exothermic. It's going to be more ordered. Right? So it's going to be exothermic. It's going to be a little bit more ordered, so our entropy is going to decrease, and our delta G is going to be negative. So if we got a following system at equilibrium at 25 degrees C, where phosphorus trichloride and chlorine gas give you phosphorus pentachloride, we got a delta G of minus 92.5. Right away, we know that it's going to be spontaneous, right? That's our spontaneous reaction. What will happen to the ratio of the partial pressure of the PCl5 to the partial pressure of the PCl3 if the temperature is raised? And we're going to explain that using thermodynamics, right? So, before we were saying, okay, well, heat's a product or heat's a reactant. What's Le Chatelier's principle going to do? Now we're going to look at it from this thermodynamic energetics point of view. Delta S is going to be negative. It's unfavorable because we're going to fewer moles of gas. We got 2 on the left and 1 on the right. Right? We're going to end up with a negative delta S. Right? So our delta S is negative. So delta H over here has to be, negative. So in order for it to be spontaneous, delta G has to be negative. And if delta S is going to be a negative times a negative or a positive, it means that overall this guy's got to be both negative and larger in magnitude than our T times delta S. Delta H has to be negative, right? Exothermic, which is a little bit more favorable. Then the temperature is increased. The reaction is going to proceed to the left, decreasing the ratio of the partial pressure of PCl5. So the partial pressure, so the ratio of the partial pressures to the of the PCl5 to the PCl3, the ratio will decrease. Right?